Hello class, today we're continuing with electrochemistry and talking about standard reduction potentials, which are the way that we quantify how difficult or how easy it is to reduce something. Something that is easier to reduce for a galvanic cell is going to be our reduction reaction, which is the cathode, and something that is more difficult to reduce is actually going to end up being our oxidation reaction, which is going to take place at our anode. The way that we quantify standard reduction potentials is to reference them to a reference electrode. All reduction potentials, as we're going to see, take place with a negative potential voltage because we're adding electrons to things, and having the presence of electrons in solution or things like that requires a negative potential because electrons are negatively charged. But what's going to be important to us is how they compare to a reference electrode. So for example, the reference electrode that we're going to be using in aqueous systems is the standard hydrogen electrode, which is the reaction of two protons, 1 molar, being reduced by two equivalents of electrons to form one equivalent of hydrogen gas, and we impose a 0 voltage on that. So if something's easier to reduce than the standard hydrogen electrode, it'll have a positive voltage. If it's more difficult to reduce, it requires a more negative charge, more electrons in solution, so it'll have a negative voltage. So for example, manganese 2 plus is reduced by 2 electrons to form manganese solid. That has a standard reduction potential of negative 1.185 volts versus the standard hydrogen electrode. It is more difficult to reduce than protons, so it requires a more negative potential. Iron 3 plus gets reduced by 1 electron to form iron 2 plus. That has a standard reduction potential of positive 0.771 versus the standard hydrogen electrode because it is less difficult to reduce than protons and requires a less negative voltage. So why do I say things like less negative and more negative? It's because overall in solution we're at a negative potential. And the reason for that is because we're adding electrons to things. So if we go to page 110, we're going to add a little bit of notes here so that we can see a graphic of exactly what we're doing. So if we take in brown here 0 to be a neutral charge in solution, if we're reducing things, we need to add a negative potential because we're adding electrons. So all of these reactions that we're talking about have a negative potential. But where we are in this negative zone is completely arbitrary unless we reference it against something. And by arbitrary, I mean not reproducible. Here, what we see is the standard hydrogen electrode showing up somewhere in this negative potential region. Manganese 2 plus, as we just saw, is more negative because it's more difficult to reduce. So it gets a negative voltage versus the standard hydrogen electrode. Iron 3 plus is easier to reduce, so it's positive. And this distance between iron 3 plus and the standard hydrogen electrode is reproducible. This distance between the standard hydrogen electrode and the manganese 2 plus is reproducible. But overall, these three things can shift a little bit. So we really absolutely need to reference things to a reference electrode. And as we go more negative, it is more difficult to reduce something. Because if it's difficult to reduce, it might go negative charge, negative charge, negative charge, negative charge, and then you add an electron. For iron 3 plus, it's negative charge, and the electron goes on because it's easier. Okay, returning to our standard reduction potentials. So in this situation, we have manganese 2 plus being reduced to form manganese solid. We have iron 3 plus being reduced to form iron 2 plus. So overall, the cell potential can be calculated for the entire reaction, which would be in this case manganese and iron reacting with one another. The overall E cell is going to always be equal to our E cathode minus our E anode. So the reduction potentials of the half reactions. So that's these values over here. The question is, for all of these reactions, is which one is going to be the cathode, which one is going to be the anode. In example 3, those are presented for us. If we look at the standard cell notation, we can see that for a reaction of copper and silver, we have copper being oxidized to copper 2 plus. That's our anode. It's an oxidation reaction, which has an E cell of positive 0.337 volts versus the standard hydrogen electrode. And then we have a reduction reaction, which is silver being reduced to silver solid, which is our cathode, which has a reduction potential of positive 0.776 voltage. So our E cell is going to be 0.796, 0.7996, minus our anode, 0.337. So our E cell is going to be equal to 0.463 volts for this entire reaction. So how do we figure out, if we don't get presented with this sort of form, which compound is the anode and which compound is the cathode? Well, in an example here, we have the half reaction containing platinum to platinum 2+, and a half cell containing chromium to chromium 3+, and they're connected with a wire and a salt bridge. And what we need to do is define the cell with standard cell notation. So first, we're going to write everything as a reduction potential. That's how we do things. Everything gets referenced to how well or how difficult or how easy it is to reduce something. Similarly, in an analogy to acid-base chemistry, everything is written in terms of the pH scale, in terms of how acidic something is, even if it's not acidic at all, even if it's a base. In electrochemistry, we write everything in terms of the reduction potentials. So that's just how it is conventionally. So what we're going to do is define the cell. So platinum is getting reduced by 2 electrons to form platinum solid. That has an E cell of positive 1.20. Chromium 3+ is reduced by 3 electrons to form chromium 0, which has an E cell of negative 0.744 volts. So those are our two reduction potentials for those two reactions. What we need to do is figure out which one is going to be the cathode, which one is the anode. If we were combining these and showing an overall reaction, once we identify the anode, we actually have to flip it because the anode's an oxidation. But we'll get to that in a second. So let's look at the numbers. The numbers tell us. So given a negative voltage versus our standard hydrogen electrode, that means that it is more difficult to reduce. A positive voltage versus our standard hydrogen electrode means that it's less negative and easier to reduce. The thing that is easier to reduce is going to be our reduction reaction because it's easier to reduce. So that's going to be our cathode. By deduction, we can then decide that the more difficult to reduce thing is actually going to be our oxidation reaction, which is going to take place at the anode. Once we've decided this, we can just write our standard cell notation and write the chromium reaction going from chromium 0 to chromium 3+ is our anode, and platinum 2+ to platinum 0 solid is our cathode. So the platinum reaction doesn't change. We've determined that the platinum reaction is our reduction reaction. It's taking place at the cathode, so it looks just like our reduction potential. However, the reaction taking place at the anode, the reaction that's more difficult to reduce, therefore an oxidation, we flip the reaction in order to put it in our standard cell notation, because what's happening when these things react is chromium is being oxidized. So now we calculate the E cell. E cell is always going to be equal to cathode minus anode, so that's going to be 1.20 volts minus negative 0.744 volts, so the E cell is going to be positive 1.94 volts. So what do we do with this information? That has to do with the Nernst equation, which relates the cell potentials to free energy changes. So, for example, delta G naught under standard conditions is equal to negative N times F times E cell. And E cell we were just able to calculate from our voltage, standard reduction potential voltages, being cathode minus anode. In this equation, the new compound, or the new variables rather, are N, which is going to be our moles of electrons, and F, which is Faraday's constant, which is a value that's 9.648 times 10 to the fourth joules per volt per mole. So let's look at an example where we have to calculate the delta G for the following reaction, where we have tin going to tin ion, which is going to be our anode, and copper getting reduced to copper solid, which is our cathode. So our anode is going to have a reduction potential of negative 0.1262 volts, where we are losing 2 electrons, and our cathode is going to have a reduction potential of positive 0.337 volts, which is gaining 2 electrons, so as copper gets reduced by 2 electrons to form copper solid. This reaction is already balanced, so our moles of electrons being transferred is equal to 2. We have 2 equivalent electrons being transferred. So let's use all of this information. So we have our E cell, which is going to be equal to our cathode minus anode, and for this reaction is going to be positive 0.463 volts. We can then use our delta G equation, which is going to be equal to negative N times F times E cell, which is going to be equal to negative 2. There's a typo here. That mole should not be there. Delta G is equal to negative 2 times 9.648 times 10 to the fourth joules per volt per mole, plus multiplied by positive 0.463 volts. So the volts cancel, And what we're left with is a delta G that's equal to negative 89,340 joules per mole, or negative 89.63, or 89.3 kilojoules per mole. So what does this mean? This means that when we have a positive E cell, so anytime you have the cathode minus anode gives you a positive number, what ends up happening is you have a positive value, a positive value, a positive value, and a negative in front of everything. So every time you have a positive E cell, you get a negative delta G. So a positive E cell indicates a spontaneous reaction because delta G is always going to be negative in those situations. Now we can also relate our cell potentials to equilibrium constants using this triangle of reactions provided. So first, we also have a equation from earlier in the semester where delta G naught is equal to negative RT ln K, where R is the gas constant, 8.314 joules per Kelvin per mole, and our T temperature is in Kelvin. So if we have delta G is equal to negative RT ln K, and we have delta G is also now equal to negative NFE cell, we can plug in negative NFE cell in for delta G, and we get this equation here. And then what we can do is isolate this variable. So we take the right side of this equation and divide by negative NF, and what we get is E cell is equal to RT divided by NF times the natural log of K. So in this way, we can take an equilibrium constant and then relate it immediately to E cell. We can take E cell and relate that to delta G. So all of these things now are delta G, our Gibbs free energy change, our equilibrium constant, and our E cell are now all completely interrelated together. And those three concepts account for most of this semester. So let's take a look at how these are all related. If we go between delta G and K, we use delta G equals negative RT ln K. We go from delta G to E cell, that's negative NF E cell. And if we go from E cell to K, that's E cell is equal to RT over NF times ln of K. So all these things are interrelated with one another. Let's move on and take another example where we have a standard cell potential, or standard cell notation, which indicates a galvanic cell of aluminum solid getting oxidized to aluminum 3+, which is in solution with a concentration that's equal to 0.15 molar. And then we have copper 2+ in solution with a concentration of 0.025 molar being reduced to copper solid. The left side is always our anode, the right side is always our cathode. The left side is our oxidation, the right side is our reduction. What's interesting here now is that we have concentrations in solution of our two galvanic cells that are not equal to 1. That tells us that we are at non-standard conditions. So we can use this information to figure out if the reaction is going to be spontaneous or not. So how do we do that? So first we need the cell potential at room temperature. So we have aluminum 3+ getting reduced to form aluminum solid that has an E cell that's equal to negative 1.662 volts. We have copper 2+ that's being reduced to form copper solid, which has an E cell that's equal to positive 0.337 volts. What we can do in order to get an equal transfer of electrons is we're going to have to multiply or cross-multiply these reactions to get an equal transfer of electrons. But we do not change our E cell values. That goes back to a little blurb that was earlier in the packet that says that these reactions are intensive properties. They do not depend on the stoichiometry of the reaction. So the standard cell potentials always stay the same, even if you have to cross-multiply to get an equal balance of electrons. So our E cell is going to be equal to our cathode minus anode, which is 0.337 minus negative 1.662, which gives us a positive number. The positive number is going to be very useful to us, but remember that this is not under standard conditions. So this is not the same as this E cell. Okay, so what do we do next? We need to figure out N in order to use some of these equations. So how do we figure out N? This is where the cross-multiplying comes into play. So we have aluminum getting oxidized by 3 electrons and copper being reduced by 2 electrons. So we cross-multiply, and what we get is 2 equivalents of aluminum get oxidized to 2 equivalents of aluminum 3+ and produce 6 electrons. 3 equivalents of copper 2+ get reduced by 6 electrons to form 3 equivalents of copper. So our reactants for this reaction, we have 2 equivalents of aluminum reacting with 3 equivalents of copper 2+, and our products, we form 2 equivalents of aluminum 3+ and 3 equivalents of copper 0. We have 6 electrons being transferred, which cancel, but that 6 is equal to our N. So we're not under standard conditions. which means that when we go and look at a equilibrium constant, it cannot be equal to K. So when we do that, we'll find that it is Q. Q is our equilibrium constant, not under standard conditions. So we have Q is always going to be equal to our concentration of products over reactants. The net reaction that we just figured out is equal to our products, 2 equivalents of aluminum solid reacting with 3 equivalents of copper 2 plus. That's what we figured out here, where we had our reactants. And then those create our 2 products, 2 equivalents of aluminum 3 plus and 3 equivalents of copper 0, which are here. Provided in the problem are 2 concentrations, 1 concentration for aluminum 3 plus and 1 concentration for copper 2 plus. So we can put those concentrations right underneath the 2 compounds that are actually in solution. So when we look at Q, it's going to be equal to the concentration of our products, our aluminum, divided by the concentration of our copper, shown here, our reactant. The copper solid in the product and the aluminum solid in the reactant do not come into play because they are solid and they are not in solution. So remember, when we're doing equilibrium constants, it's only things that are in solution. So our Q for this reaction is going to be equal to the concentration of aluminum 3 plus, our product, squared, since it has a coefficient of 2, divided by the concentration of copper 2 plus, our reactant, cubed because it has a coefficient of 3. We bring in these values for 0.15 and 0.025, and we end up with a Q that's equal to 1,440. And we're going to pick this up next class.